Hey guys, welcome back to another episode of Simulayos. Today's going to be rather interesting. We're not working on the determinate visualization anymore. I'm content with how that video is turning out. It's 2 minutes and 45 seconds long, which is a little short, admittedly, but hey, that's how it goes, you know? Sometimes videos just don't end up being that long. And honestly, guys, I don't know about your opinion, but my opinion is that shorter videos are better. I like shorter videos. People respect my time. I respect their time. I think it's fine. Now, that said, I understand the reason for having longer videos, and in the future I might make some longer YouTube videos again, but you know, the way I see it is I have this stream, and if I ever want to randomly ramble in front of a microphone, they can just watch me on my Simulayos channel. I see no reason why I should have separate videos on YouTube of me just talking for 20 minutes. I don't think it's as relevant anymore. Okay, so what are we doing today? Today, we are hopefully going to move straight into, well, not straight into, but we're going to move into the Huffman trees dynamically. So, as a reminder of how far we've gotten, we spent maybe 2 to 3 days coding up our first Huffman tree, and then maybe 10 days coding up our first Huffman tree visualization. Let's CD into projects, Huffman, and let's see how it turned into, projects, Simulayos, and then Huffman, and let's see how it looks. Because honestly, I think it looks pretty dang good. So let's do Mirage, frames, animation.gif, and this is what we've got. So here, you can clearly see all of the dots being created, all of different colors symbolizing their weight, and then all of our lines going through and basically reading out exactly what each of these letters mean in their encoded scheme. This gives people, I think, a good intuition as to how the Huffman algorithm works. Now, let's scroll down a little bit to where we see the blue here. Now, at this point, there was a suggestion made by someone in chat a while ago. Unfortunately, I don't remember who it was, but definitely someone in chat. What I need to do is I need to add in a small weight for each of these nodes. Now, the weight's not going to be that big, but we do need to add the weight. That's one thing we need to do first. Hey, Mr. Miyagi, what's up? So then the other thing I need to think about is what I want to do with these internal nodes. On the one hand, I kind of like the fact that these internal nodes are not drawn. But when we do the dynamic Huffman algorithm, we might want to draw them. In fact, there is some other information that we might want to draw onto this plot, and we have to think about how to do that. But first things first, let's see if we can add in a very small weight to each of these nodes so that people understand what these nodes mean, kind of, I guess, numerically, if that's the word I'm looking for. Okay, so as always, let's start by opening up Zernal and talking about what we need to do today. We're going to open up Zernal again later in the episode. We start talking about the dynamic Huffman tree because, quite frankly, it is a big pain to understand. I'm not even trying. Gosh. So this algorithm that I'm using for the dynamic Huffman tree is, first of all, absolutely brilliant. It's a fantastic algorithm. I think it's great. On the other hand, wow. It took me 2 weeks almost to figure out how it worked and what it was doing. I mean, the first day I did Huffman encoding. If you go back to the very first video, it's archived on YouTube. Hey, Gustron, I said we're going to move into dynamic Huffman coding, and I said, well, we need to think about how we're going to do this for dynamic Huffman coding, yada yada yada. And then Gustron convinced me, hey, we're going to do this for a simple Huffman tree first. I was like, yeah, okay, but we have to always think about this dynamic Huffman tree. Finally, I think I have an okay grasp on how this algorithm works. I haven't tested it with too many trees, but what we're going to do first is describe basic Huffman encoding, do what we need to finish up there, and then we're going to come back to dynamic Huffman encoding probably in 30 minutes to an hour. Now, as you learned yesterday, anytime I say something's going to take an hour, assume it's going to take longer than an hour, but I hope that today's episode's not going to take that long. Okay, yeah, right, Gustorn? Okay, so let's go ahead and get started then. For a simple Huffman tree, let's talk about how it works. So first things first, let's say we're getting a random string of letters. Okay, so these letters are just being read in through the phone. Someone's just saying, you know, it's like a WAP old passphrase, you know? So it's like people are calling in letters and they're just like, okay, A, B, Q, Z, 9, 12, 7, 15, something like that. And I guess 12 doesn't count because it's 2 digits, but you know what I mean. Everyone's sending in a whole bunch of letters. And let's say they send in letters with a frequency of, I don't know, A with a frequency of 60%, B with a frequency of 25%, C with a frequency of, I don't know, 0.5%, D with a frequency of 0.5%, and E with a frequency of 0.5%. That adds up, right? Sure, why not? Okay. And in fact, let's change these around a little bit. Let's do all these 10. These are all going to be 10. So 10, 10, 10, 10, dot, 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 dot. Okay, so this is how we work with simple Huffman trees. We take the two lowest values, we add them together to make 0.2. Take the two lowest values, we add them together to make 0.2. Take the two lowest values, add them together to make 0.4. Take the two lowest values, add them together to make 1. Then we go back and we read the tree. So 1, 0, 1, 0, 1, 0, 1, 0. Then we say A, reading backwards, is just 1. We say B is going to be 0, 1, 1. C is going to be 0, 1, 0. D is going to be 0, 0, 1. And then E is going to be 0, 0, 0. There we go. That's our code. So if we get a phrase of, I'm going to put it up here, A, B, C, D, E. It's going to be 1, 1, 1, 1, 0, 1, 1, 0, 1, 0, 0, 1, 1, oh, 0, 0, 1, sorry about that. And then 0, 0, 0. And that is our encoding phrase. And that's exactly how the Huffman algorithm works. Now, what we have right now is a pretty good visualization of how to draw a Huffman tree. This is great. However, let me try to motivate what we're going to be doing later on in the episode. So let's say we have a very long string. A, B, C, D, E, F. Oh, let's say we keep with these letters. B, B, C, C, B, B, C, C, D, D, A, D, D, C, C, C. Okay, so let's see what happened. At the start, we have 4 A's, B, C, D, E. Okay, so this 1, 2, 3, 4, 5, 6, 7, 8. Okay, this is roughly the same frequencies we were working with before, right? We have 4 A's, 1 B, 1 C, 1 D, 1 E. Okay, so this means A comes up with a frequency of 50%, and all the others come up with a frequency of, well, less than 50%. Okay, but now let's see, we have 3 B's, 2 A's, so now the frequency has changed. A is still dominant, but just barely dominant. Now we have 3 C's, 3 B's, and 4 A's. So now A is not quite as dominant as it was before. Now at this point, we have more B's than we have A's. And here we have more C's than we have A's. Here we have the same amount of D's as we have A's. Mr. Miyagi, is it F, G, H values? Let me see. If you can reference the description of the algorithm, it's pretty easy to garbage collection language. Moderately difficult in C and C++ if you don't want to leak memory. Mr. Miyagi, are you talking to me or Gus Torn? F, G, and H values. Oh, I don't have F, G, and H values, so it must be Gus Torn. Okay. Then at this point we have more D's than A's. Basically, and at this point we have way more C's. So that's the idea. At the start, it makes sense for A to have the least number of bits. Let's say up to maybe this point. No, even further. Up to this point, it makes sense for A to have the least number of bits. It's okay, I got it. Bits. However, after this point, it no longer makes sense because A is no longer the most frequent letter anymore in the alphabet. Remember, the idea behind Huffman encoding is that we take all of the bits, or rather, we take all of the letters, we find their frequencies, and then we minimize the number of bits in the end. So the letters with the highest frequency, the ones who show up the most, should have the lowest number of bits, so that as we go and encode the phrase, let me think. So as we go and encode the phrase, how do I put this? We use less bits in the end. And that's the idea. So the problem here is no matter what, in this code, we're going to be inefficient. So here we'd say, okay, well, A should probably be the least number of bits. However, from here, it should not be the least number of bits. So A is not, forgive me for my notation. I'm just going to write top like that. Okay, so here's the idea. A is the least number of bits. A is no longer the least number of bits over here. So if we have a static code throughout this entire, if we have a static encoding scheme for this entire string, there's going to come a time when all of a sudden the encoding string is no longer effective anymore. And that's the idea with dynamic Huffman encoding. What we're going to do is we're going to create an encoding scheme in a dynamic way that takes into account all of the letters that we've seen so far, not just the entire string. And this should, if done correctly, minimize the number of bits in the long run. And that's really, really kind of cool. Now, how to do this? We'll leave that as a cliffhanger. So hopefully we'll get to this today and you guys will be super amazed. There are multiple ways to do a dynamic algorithm like this. I want to do dynamic Huffman because we already have the ability to draw Huffman trees, and I really wanted to see a Huffman tree be, grown. I've always kind of wanted to see that, just because I think it's kind of neat, growing Huffman trees. Okay, so I'm going to get a quick sip of water, and then we'll get started with the rather, I believe, straightforward stuff of today's episode. Now, we're going to see how far we get. It might be that we don't actually do any coding of the dynamic Huffman tree today. It could be that instead we spend the entire time working on, well, what is essentially the blackboard, as in my little journal page here, to describe what it is that we're talking about and stuff like that. So we'll see how far we get. But first things first, we do have a bit of coding. We'll see how long it takes. All right, again, quick sip of water, and then we'll go ahead and get started. Okay, let's bring this over there. Again, this is the animation that we have so far. Straightforward distance to be proven always admissible in Euclidean space. Okay, this animation looks pretty dang good. I am super excited with this. Like, this is something I would show my mother and she would put on the fridge. I mean, it's an animation, so she'd have to put a lot, there's 300 frames here, right? So I guess she'd tape all 300 frames to the fridge, which would be a little weird, but hey, I'm not, she was weird. We weren't a normal family, so maybe this is something that she'd just print out all 300 frames and she'd put it on the fridge. Maybe that happened. I don't know. Anyway, let's go ahead and CD into the appropriate directory. CD projects, Simuleos Huffman. Okay, so as I said before, the one thing I want to visualize right now is putting the weights on each of these little dots. And that shouldn't be so bad. All we need to do is go to each individual orb and put a number on it for the weight. So every time we draw a circle, we also put in the weights. So let's go here. VI Huffman. Visualization, sorry for the hiccup, guys, .cpp. Okay, so now we have to, let's see, grow circle. Let's see, I don't want to put in the grow circle command. I need a different command for this. So drop text. Let's go down and function to place the weights. And what do I need? So void place weights. I guess I should have it draw weights. Draw weights. Okay, and what do we need for this? So small report on my web dev adventures. Man, my Git changes are disgusting. There's so much boilerplate. I worked on a single feature day. I have 120 changed files. Holy crap! 120? Holy crap! That's like more. That is more files than I worked on lines in my last, like, yesterday during work. Of course, yesterday I was working on a, I wasn't working on coding. I was working on something else. But still, that's beside the point. Draw weight. So what do we need? For this guy, we're going to need frame, animation. Okay. Then we want std string code word. Nope, we want the weight itself. So let's do, oh, I think I have this saved somewhere. What do I have? Let's just do std string weight. Let's see, double weight, position ori. Yeah, let's do position ori, double weight. Yeah, so we could do that too. Wait, we're reading in the weight. Oh, let's just do double weight. And the position origin. Okay, good. Is it just me or has web dev become overly complicated now? I think, if I'm not mistaken, there was a conversation I saw on, oh, where was it? Was it Reddit? It was somewhere about how web development has become incredibly complicated, and I would totally agree with that. It's one of those situations where you know, or at least in my opinion, you know specific tools and you can use those specific tools, but it's incredibly hard to generalize because the tools are consistently changing and everything is just rapidly evolving, you know? With my line of work, everyone's still using Fortran, so who cares? With other people's lines of work, I get it, you know, like, so even the modern computer science world that's not web development advances faster than my line of work, you know? So that's how it is. Oh, by the way, guys, if you're watching and you have any questions, let me know, and I will totally get to those questions as soon as I see them in chat. I do my best to answer the questions as honestly as possible. I don't try to pretend I know things I don't know. So if you say something, even if it's rather embarrassing that I don't know it, I will let you know that I don't know it. If I think I know it and I don't actually know it, I will try to tell you the answer and then halfway through realize I don't know it, and then I'll explain why. So anyway, that's how I do questions, letting you know. Draw weights. Sorry to derail you, but what did I miss yesterday? Oh, yesterday we didn't miss so much. So what we did yesterday was we went through and finished up a visualization I needed for my determinant YouTube video, which is coming out on Sunday. The reason I had to do it on stream instead of off of stream is simply because this weekend I'm teaching a course for OIST. So I did not have time, or I will not have time to do all of it then. Normally I would spend basically the entire day Saturday working on that, but I have to kind of do it throughout the week. So I took a day off, spent some time working on that. It turned out okay. I was happy with it, but I screwed up in the end, as it always seems I do, and I tried to visualize something that actually was not physically applicable. So that's okay. At least I learned how it was fixed, and so I didn't put this one up on YouTube, that one up on YouTube, because it was kind of a side topic, and it wasn't exactly, I think, worth people necessarily rewatching. So that was kind of what I did there. But yeah, so it wasn't that much. Okay, so draw weights. Let's go down to the bottom. That was a big G. 1 second. So what I tried to do, here, I'll show you those visualizations. So here's what we did yesterday. CD projects. Let me see, where are we? We're in Huffman. So I think it's gonna be under visualization and determinant. So for the determinant video, we have a couple of different ways to show how to get a determinant. The first way is the most obvious way, which is simply to calculate the determinant. Most people know how to do that, so I don't spend any time in my video explaining how to do that. In fact, I think I'm going to keep my videos mostly just explanations or like intuitive pictures instead of like explanations of how to do things. And I think that's the best way to do it, because if people want an explanation of how to do things, honestly, I don't get that information from a video. What I get from a video is physical intuition, you know? What I get from textbooks is methods and things of how to do things. So that's my personal opinion. It's easier for me to figure out things when I see a problem in front of me and I just try to work on the problem. And that's not what you can get in a video. Anyway, that's beside the point. Okay, so there's also two other ways to find the determinant. The first way is relatively straightforward. All we have to do is basically transform a box, and then after the box is transformed, go back through and find the ratio of the new transformed box to the old box before transformation. And this is shown here. So let's do Mirage, mPlayer. Let's say angle 1, why not? .mp4, VOX11 so you guys can see it, and of course loop 0 so I don't have to keep replaying it. F. Okay, so let's go back to the very start. Here's our original box. Here's the transform box after matrix multiplication. And then there's the original box, and we put an extra box on the outside. We then perform Monte Carlo integration, which I think looks pretty good. And we get this in the end. Sorry about the lines in the middle, but we get this in the end. If we take a ratio of the yellow to the red, we'll find that the ratio is basically 9 to 1, right? So we have 9 times as many dots in the yellow as we have in the red, right? So this is for a transformation matrix that we typically use, which is, here, let's just let it play for a little bit. Our typical, let's see, 1, 2, 0, 2, 1, 0, 0, 0, negative 3. Okay, so the next visualization is just that from another angle. Let's go here. Which again, I think looks pretty good. I think that yellow needs to be more yellow, but we can work on that in a second. So I'm going to be showing both these visualizations at the same time. Another way to find the determinant is by multiplying, or I'm sorry, working with the following. So if we do angle 1, eigen.mp4, the idea here is that we start with some sort of cube in space, here. We perform a transformation, and we get another cube out here. Now what we do is we multiply the length, width, and height of this new cube. Now you might be thinking to yourself, wait, we just did this. We just did a transformation. We just created a new cube, but then we had to do some sort of numerical integration scheme. Well, this one is a little bit different. We align the cube to what are known as eigenvalues. And during a transformation, eigenvalues only stretch. They don't at all change direction. And because of this, the cube itself will only stretch. It won't change directions, which means when we get to this point here where we have the original cube and the new cube, the ratio between the areas, because again this was a unit cube of length 1, length, width, and height 1, will simply be the length, width, and height of this new cube, which happen to be eigenvalues. So 3 ways to find the determinant. 1, transform an object, find the ratio of the volumes. 2, actually perform the determinant, which is relatively straightforward. Or 3, align the cube, or align the object, well, align a cube along the eigenvectors, transform it, and then multiply together the eigenvalues. And that's the third way to find the determinant. So it's a multiplication, a product of all of the eigenvalues. And that's pretty cool. I like that. Okay, so what I say when it wasn't physically applicable, I was trying to do something really stupid. So here's our transformation going on, right? It's obvious that the lines are stretching and also moving. However, they're not rotating, right? So eigenvectors, they can move, obviously, but they simply cannot rotate. What I was trying to do was set the positions of each of the eigenvectors such that they would only stretch into the cube, right? So I wanted to make this final cube, let's see, somewhere in here. I wanted to make this final cube without starting with the unit cube, which doesn't actually make physical sense. I was completely off my rocker there. I was wrong. I was just trying to do something kind of silly, just to show that any arbitrary object can be transformed. And I did something really stupid there. So anyway, that visualization is not going to be there. This is for a yes, it is a 3x3 matrix determinant. Again, the determinant of the matrix of the following. So it is, let me see, new page before, 1, 2, 0, 2, 1, 0, 0, 0, negative 3. And if we perform the determinant, it's going to be 1 times 1 times negative 3 minus 0 times 0 minus 2 times 2 times negative 3 minus 0 times 0, and then plus 0 times 2 times 0 minus, let me see, 1 times 0. So this one's just 0, 0, 0, so it's going to be negative 3 plus 12 equals 9. The determinant of the matrix is also the volume of the parallel pipette formed by the vectors in the rows. The determinant of the matrix is also the volume of the parallel pipette formed by the vectors of the rows. Yeah, that's exactly what we showed first. Exactly what we showed here. So that's what we're showing here with this visualization. In the end, what we've done is we've drawn the same thing, right, as what you're saying over there. So it is that. So that's one way to find the volume here. Assuming you start with a unit cube. Then yes. Okay. So then the next is a multiplication of the eigenvalues. Wait, really? I thought that was pretty obvious. The animation... Huh. Wait, let me see. The determinant of matrix is also formed by the parallel pipette formed by the vectors in the rows. Oh, actually, no. It is a different thing. Sorry. Let me think. So what you're saying is if we... Is that true? Oh, I never thought about that. So if we do a... Let's see. So it'd be 1 in X, 2 in Y. Let's see. Huh. Maybe that is true. I never really thought about that. So let me think. So what you're saying is if we draw out each of these vectors, 1, 2, 0, 2, 1, 0, 0, 0, negative 3. So that would be basically 1 in negative 3, 1 this way, and 1 this way, or something like that. And you're saying if we draw a cube here, something like this. Sorry, I can't really draw. That this will be the determinant, the area inside of here. Oh, okay. Interesting. Yeah, that's different than what I was thinking. Let me see something. So if we perform a transformation on a unit cube, what does this turn into? It turns into a matrix where we have 3 in this direction. Let's see. 3 in this direction. Let me see. We have... Wait. This guy stretches by negative 1. This guy stretches by 3. Actually, that is, I think, exactly what we're showing, in a way. Let me think here. So the matrix that's being transformed, right? We perform a matrix transformation. And the matrix that we started with, or the matrix that's being transformed, is simply of size 1 in X, Y, and Z. So we have, basically, we are transforming 3 different points, and these points are let's see, 1 in X, 1 in Y, and 1 in Z. So in the end, we actually get that parallel pipette that we can use to find the volume. Yeah. Actually, yeah, it is the same thing, I think. Because I think this is the parallel pipette, because it's negative 3 in the, let me think. It's negative 3 in the Z direction, which is exactly what you'd expect. Then it's also, let's see, if we look at it down the line, it should be, we should have a 1, 2, and a 2, 1, which is exactly what we see. So let me think. We started there. Yeah, so then that guy shifts to up 2, over 1, over 2, up 1. Yeah. Okay, good. So it is actually what we see. Yep. Yeah, good. It is easier to visualize in 2D. However, I guess I can add in a quick... Yeah, I should probably add in a quick voice clip there saying that this is basically the same thing. Okay, thanks for that. I appreciate it. Okay, so let's see what we need to do. Let's go back to the draw weight stuff. I apologize for the sidetrack. Let's see, we started with the sidetrack, I guess, like 10 minutes ago. My apologies. Okay, so let's CD back a couple directories into Huffman. Let's take a look at the image again. Okay, so now we have to draw all the weights. So let's go ahead and do that. So let's see, drop text. We have this guy. That's not too big of a deal. Let's go here. And basically now we just have to put in all the weights. So let's do it. 4. And we're gonna put in all the frames. So we have to go through all the frames. So 4, size T. Oh, that was a capital T. I equals 0. Oh, that was the wrong button. Let's do I less than, what do we want here? Number of frames. number of frames. Okay, 1 second. Plus plus j, or plus plus I. A three-dimensional matrix is, I mean, the same as a two-dimensional matrix, right? So let's just take a second and look at this. So, new page before. Here's the idea. If we have a, let's say two-dimensional matrix of 1, 2, 2, 1, this is going to be x, y. So we have, here is our plot. 2, 1 is going to be 1, 2, up 1. The other one's going to be up 2 over 1. So here's our matrix, right? Yeah. So what was said before was that by finding the area of this guy here, we can find the determinant of our matrix, which is no different than saying if we add in, let's say 1, 2, 2, 1, multiplied by our vector of 1, 1, which is going to be our unit vector, we'll get 1, 2, 2, 1. So we should get, let's see. Wait, what am I doing here? 1 second, let me think. Oh, we have 2 different points, obviously. Okay. Yeah, my bad. So if we take 1, 2, 2, 1, and we transform essentially what is the identity matrix, I think this is right, we're going to get the same matrix out, which is here. Let me think. That doesn't make any sense. What am I saying here? I'm saying that... Oh, this is how we get these points up here. But that's fine, because this is an obvious point. Never mind, forget me, I didn't say that. But anyway, so you draw a two-dimensional matrix in that way. A three-dimensional matrix. If the initial cube is a unit cube, then 3 sides can be represented as the vectors. Yeah, exactly. Yeah, that's exactly right. So, yeah. Okay, yeah, maybe that's a better way to do it. So let's do 1, 2, 2, 1, and let's multiply it by 1, 0, which is this point right here. Let's draw that in red. This point right here. Okay, if we multiply it by 1, 0, we're going to get 1, 0, 2, 0, which is going to be equal to, wait 1 second. This is going to be equal to 1, 2. Yeah, there we go. The determinant of 2D is equal to the z coordinate of the cross product of both rows as z vector. The determinant of a 2D matrix is equal to the z coordinate of the cross product of both rows as three-dimensional vectors with z of 0, which is also equal to the length of both multiplied by the sine of the angle between them, thus giving the area of the parallelogram. Let me think. So you want to do a 2D matrix, and you're saying equal to z coordinate, the cross product of both rows as, 1 second, let me think. So what you're saying is, cross product, let me see, of both rows as 3D vectors with z equals 0. Okay, so we're saying 1, 2, 0, 2, 1, 0, x hat, y hat, z hat. Then we have, let's see here, there's nothing in x hat, nothing in y hat, only something in z hat, which is exactly the determinant, so that's obvious. Yeah. Yeah, well, I mean, yeah, this is actually incredibly, yeah. So, basically I'm just linking the area of the parallelogram to the determinant. Yeah, that's, in fact, you have to perform the determinant calculation in order to find the determinant in this way. So, I suppose it's, right, because here it's going to be nothing in x, minus nothing in y, and then it's going to be something in z, so we'll say z hat, but this is exactly how you calculate the determinant of 1 minus 4. So, it's kind of like, okay, well, okay, that's fair enough. Okay, that's fine. Let me think. Yeah, yeah, that's fine. Okay, yeah, which a cross product is something that I wanted to get into a little bit later. A cross B is equal to A times B sine of theta. Let me think. Okay. So wait, how are you going to do A times B sine of theta if you don't have a theta? 1 second. If you only have 1, 2 and 2, 1, how on earth would you calculate the cross product in that way? Oh, are you looking for? Wait, maybe you're looking for... 1 second, cross product. AB sine theta. Let me think. Angle between the vectors. Yeah, that's fair enough, I guess. But how are you gonna... Okay, so the angle between the vectors then. Okay, so let's see if we can figure this one out then. If we do this, do one here, one there. How do you find this angle? I guess if you know the two angles, you could subtract it. So you could say, okay, well, we know this angle and that angle, and we could subtract it to find the middle angle. Let me think. Wait, I'm trying to think. So what you're saying is that if we somehow find the angle, we can go from there, and that's fine. But let me think. Then you'd say AB. So we're looking for something that's equal to -3, or I guess 3 in general. So what we need is to find the angle between these two vectors. Okay, what's the magnitude of these two vectors? The magnitude is going to be x squared plus y squared. So these guys are both going to be the square root of... wait. Yeah, it's the square root of x squared plus y squared. The height of the parallelogram? Wait, what? You're saying sine theta is equal to... Or rather, A sine theta or B sine theta? Let me think. A sine theta. Here, let's draw this again. New page before. Okay, so we have a simple determinant of 1, 2, 2, 1. Okay. Let's see. So we have this. That's great. This is going to give us, let's see, 1 times 1 minus 2 times 2. So the determinant of this guy is going to be equal to -3. Yeah. Oh, is that why you do it? You get the determinant first, then you find the angle. I thought it was the other way around. I thought people wanted to find the angle and then find the determinant. No, yeah, because it makes more sense to me to just go ahead and calculate the determinant, right? Because you have your x, y values, right? So, okay, yeah, this is fine. I was trying to think to see if I wanted to add anything to the video about this. Yeah, good. Okay, so what I was thinking was that we could go back. What I want to do, I think, is do another video on cross products, where this is incredibly, like, this is one of the things that I wanted to point out with the cross product, you know? Yeah, good. Okay. Sorry about that, guys. I was getting kind of confused because I was trying to figure out how it would be more efficient to calculate the angle instead of just calculating the determinant in the first place, but that's okay. Anyway, we're incredibly sidetracked for now. Thanks, guys, for the discussion. I think what I'm going to do, I'm probably not going to change the video that I'm currently making. However, it's definitely going to be in a later video about cross products because I need to go into cross products and curls and things like that before we get into FDTD and stuff like that. So again, guys, the area of a parallelogram equals to AB sine theta, which was the point. Does that work in 3D? No. Yeah, okay, good. Okay, so here's what I'm probably going to do then, guys. This upcoming video about the determinant, I think I'm going to leave as is. I like the fact that it's a short video. Plus, I don't really have time to update the video right now. I can't, not before Sunday when I want to put it out. However, I think this is definitely something we should put into a video on cross products, which will lead into another thing. Yeah, exactly. It's already kind of what we've done. So I think I'm going to leave a note in there about it, and then we'll kind of go from there. Yeah. Besides which, if I were to visualize the 3D parallelepiped, it would be exactly the same. It would look almost identical to what we already have, I think. I'd have to think about it. Let me think about it during the day, and I'll let you guys know tomorrow if I want to do anything. We might spend a little bit of extra time on stream talking about it. Good. Okay, so back to the Huffman stuff. I apologize for taking the sidetrack again. Okay, Huffman stuff. Draw weights. Or, yeah, draw weights. What I meant is in terms of visualization, right? So the parallelepiped that I drew is the exact parallelepiped I would draw, right? However, I might find a way to like draw the inside of the cube a little bit differently, or I might find a way to create the object itself in Blender in a different way. I don't know. I haven't quite thought about how to do that. But you're right. It is the same object, Gustorn. Sorry about that. Okay, so draw weights. Let's do this. Again, sorry about being all scattered, guys. I'm all over the place right now, but that's okay. Weights. Okay, let's do it. So what we need to do is change the text size and put our weights into the appropriate location. So we already have the position origin. We have the weight. So we have how big each... Sorry about that. So we have how big each basically dot is, right? So what we want to do is put a very small white label at the top of each of these guys. Upper left-hand corner is what I'm thinking, that just has a number on it. Now, I don't really know the best way to do this. There could be other ways to visualize it. I haven't quite figured it all out. What we could do is put the weight next to each letter, which is fine. It's just, that means we have to change the way that we're visualizing all the letters. And the amount of information we're gaining from this is, though it's useful, it may not be. We'll see. We'll see what it looks like after we're doing this. Okay, so for size t, I equals 0. I list the number of frames, I plus plus. So this is basically us going through each of the phrases here. Now, how do I change a double to a char? What about below or above? We could put it below or above. We'll see. I guess what we could do is we could put down the weight directly under each of these guys, I guess, and then we could put the code under that. I know you don't. But if we have a double value, how do we change that double value into something that we could then draw on here? That's the question. I guess it turn it into a string and then turn it into a series of chars. So let me think. I know there's a way to turn a double into a string. Pretty sure I've done it before. Depends on whether you want C library or C++ one. I'd say C++. Just turn it into a string, and then after turning it into a string, we can turn it into something to visualize with sprintf. That would turn it into... Okay, let's think about it. So for size t, I equals 0. Let's just go through and figure out where we're going to put all this kind of stuff and do a couple of different changes first. So first we need to say Cairo set source RGB. RGB, and we're going to change it to animation.frame context of I, and we're going to change it to 111, which is... I see. Oh, you actually just want to write it out. Yeah, basically. It's okay. So we want to turn it to white, which is 111. And we'll try a couple of different visualization schemes. So let's see, what do we want? Set source RGB, animation frame context 111. First thing I actually want to try is something a little bit weird. So I want to try basically putting these, I think, directly under each of the nodes. I think that's what I want to try. And then we're going to put a line after that, and then we're going to put down the code word. Yeah, I mean, that's fair enough. Okay, so Cairo set source RGB 000. Now, what do we need to do next? Let's do next. Man, I'm still trying to figure out. Oh, it has 2 string? Yeah, let's use that. Why not? Okay, so Cairo set source. Cairo text extends T text box. Text extends T. And we're going to call it the same thing, text box. Go down here. We're going to say Cairo text extends and same thing. So Cairo, 1 second, text extends. Then we want animation frame context of I. Oh yeah, I is right. Test, which we don't have yet, which is fair enough. Which does not work on doubles. Oh, okay. Well, thanks for that. So we're gonna say test, and then we're gonna do at text box or ampersand text box. Okay. So what were our suggestions here? Double to string rather than double to character. That's fine. So we're gonna want. Oh, it does work. Oh, my bad. Asthea, thanks for coming in. Okay, so let's do this then. Let's say it's gonna be wait dot to string. All right, you ready? I think it's this dot C string. There you go. That's what I'm doing. Okay, we're gonna put this down here. And let's see what happens. Okay, oh. I figured that's fairly obvious. I should have figured that one out. Oh, gosh darn it, what am I doing? I don't know anymore. Wait. There we go. Okay, so that's what we're gonna do. Okay. Wait is a double, and doubles don't have any, yeah. Yeah, afterwards it's obvious. I just wasn't thinking at the time. Okay, so text extends. What do we have? Move to. Okay, so now we have to move to the appropriate point and show the text. So, hey, Zivo25, what's up? So, what are we gonna do then? Yeah, right? It looks fantastic. Okay, so let's go ahead and put this up in the upper right-hand corner for now. We're gonna change the text size, and then we will change the text size back afterwards. So let's go down here. And let's see, what is it? Font size, I believe? Let's look for it. Font size. Yes, here it is, 15. So we're going to drop it down to maybe 10 or 5 down here. There. I would rather not use boost just because it's kind of big. But let's see if this works because it seems like the simplest solution. And if that doesn't work, we'll go from there. Okay, so Cairo text extends here. So let's change the font size to, I don't know, 10. We'll change it to 10. Now, what are we going to do? We have to move to the appropriate location, which is going to be, let's think. So it's going to be Cairo move to. Let's see. Didn't large chunks of boost end up in C+ standard anyway? Could have. I don't know. Animation.frame context of I. Then we have to give it the appropriate location. So it's going to be ori.x, which is the origin of our individual dot here, minus textbox.width. .width. Yep, that's right. Divided by 2.0. Okay, so that should be our x position. But now we have to subtract out, let's see, maybe the radius divided by 2? Let's subtract out, how did I do this before? So the radius is going to be 12 plus weight of 0.05. So let's do subtract out weight times 0.5. Okay, now we're going to do the same thing for ori-y. So we're going to do ori.y minus textbox.height. Oh, I guess plus textbox.height. No, minus. Textbox.height. Then we're going to do what? Divide by 2.0? No, maybe we leave it. I don't know what I'm doing. Minus weight times 0.5. I'm just going to try this. I don't know exactly where this is going to place things because I'm really bad with Cairo text, but we'll see what it looks like. Okay, so we go here, then we do Cairo show text and Cairo stroke. What do we want? Animation dot frame context of I. Then we want toString wait cstring. There we go. Good. Don't know, never tried. You probably noticed it in millions of iterations. According to this, toString is supposed to replicate sprintf functionality anyway. That's probably pretty fair enough. Okay, so Cairo show text, and then finally Cairo stroke. And we want to stroke animation dot frame context of I. And that's that. Should have draw weights done. So what are we going to do? We're going to go up, and every time we draw a circle, let's see, where was that going to be? That's going to be a draw tree. Let's go down a little bit. Cairo text extends, Cairo stroke. Where is it? Grow circle. I know there's a grow circle command in here. There it is, grow circle. Now we're going to draw weights. So we're going to say draw weights. Did I say weights or wait? There it is. It is plural. Look at that, frame animation. Oh gosh, I'm getting really bad at this. Animation. What else do we need? We need double weight. So let's do root pointing to weight. Thanks Edison. I will fix that up in just a second. Then we need one more thing, which is what? Position origin. So then we're going to say root pointing to origin. Now let's go back and fix our draw weights command, and let's change it to std toString. And what I'm going to do is I'm actually going to go up here, so we don't have to keep calculating this because we only have one weight. So we're going to say weight text is going to be equal to std toString weight dot c string. Oh, str. Sorry about that. Good. And we're going to go here and we're going to say weight text. And we're going to see what happens. Worst that happens is it all breaks. Which, you know, we're kind of fans of on this stream. It happens all the time. Okay, so let's go here. Weight text. 1 second. Text. Write this, go over here, remove this, and let's try to run make. It's going to break, and then we just have to fix it. Okay, where did it break? Frame context. Was not declared in the scope. That's fair enough. 473. Frame context of I should be animation.frame context. This was something I clearly knew. I just wasn't thinking. Error. I was not declared in the scope. Frame context of I. Set font size. Oh, shoot. I guess this has to be in the loop, doesn't it? Darn. There. And then outside of the loop, too. Is there any way to fix this? No, I guess it's dependent on every context, right? So we're just going to have to change this every time. That's okay. So let's remove this and remove this. Hey, Edge226, what's up? Okay, so weight text was not declared in the scope. Of course not, because I don't know what I was thinking there. So it's going to be char. Oh, it's going to be char. Oh, what's it supposed to be? Is it char star? I'm going to guess it's char star. Now what's next? Or wait, y. 481. Let me see. Of course it was expecting that. 481. Oh, actually, no, it was not. It wants a comma. And 42, same fixture, same problem. Write this, go to make. Let's see, frame context. Constant char to char star. Oh. Yeah, 1 second. I think constant char star is not going to like. Frame context was not declared in the scope. It was not because I need an animation before it. Let's do animation. Make. Did it make? Yeah, okay, so now we're doing all of our frames. Should be 300 frames, and let's see where those weights are placed. This is gonna be awful. Yeah, you're right. I'm slowly coming around to auto as a thing. I don't know. It still kind of strikes me as odd. But I've been doing so much Julia and Python lately that it's kind of okay. Maybe it's worthwhile. Okay. I'm sorry. Gosh. This is one of the few times I admit that it's useful. Animation.gif. Let's see what it looks like. It looks the same. Let's see. What did I do wrong? Frame. Image is what I want. Scroll down. Yeah, okay, so I apparently did something stupid here. What did I do that was stupid? Well, besides getting up at 5 o'clock in the morning to stream, actually that wasn't stupid. This has actually helped me tremendously doing this stream. If there is no right or left, we grow the circle. It's also useful when you got hideously long template types. Okay, fine, fair enough. Okay, so what do we do here? Grow circle, draw weights. Animation, root weight, root ori. Oh. Animation, frame, context. What am I reading in? I'm reading in frame anim. But what should I be reading in? Frame anim. Let me think here. Anim, frame, context. Oh, this is exactly what I should be reading in. This is right. Anim, frame, context, J. Dang, I thought I was wrong. Okay. 111, is that black or white? I think that's white. So we set the source, RGB. Man, why is the text not showing? Okay, cover text extends T, text box, animation frame context of I. Weight text, which should be fine. Just for the record, let's see out weight text. STD, see out, weight text. Are we allowed to do this? I don't know, let's try it. Make. Yep, we totally have weights. They're exactly what you would expect. What are you calling draw weights? I believe so, yeah. I mean, that's a fair enough question. Draw weights, right here. Okay. And I just realized weight is an integer. I thought it was a double, but it's totally an integer. Okay. So that's going to make the visualization a little bit weird, but that's okay. Let's take a look. Let me see. What did we make? Image. Scroll down. Yeah, okay. So we're clearly not visualizing anything yet. Okay, so why not? That's the question. We're outputting weight text. Weight text is clearly something, although maybe not what we want. It's 2.0, 1.0, all that kind of stuff. Okay, so that's fine. Color set font size. We're changing the animation frame context font size. Which is good. We're then setting the source to white, also fine. Moving it, I'm hoping to the appropriate location. Ori.x, text box width. What are we reading in as origin? Do we have an origin to read in? Oh gosh, that's gonna be a pain, isn't it? Undo. I'm sorry guys, I was an idiot here. Let me go up here real quick and run. I'm not sure what just happened there. What is W weights? There we go. Okay. Let's go down to the bottom. I'm not sure what happened. Sorry about that. I must have accidentally right-clicked and pasted. Okay, so what are we going to do? Drop text. Drop text is working just fine, but it's a completely different bear. It's like a polar bear versus black bear and bear. Okay. Sorry. Bear with me. Oh my gosh. This is what you guys get for coming to someone who's streaming at 6 in the morning. Okay, animate line, draw encoding. What are we gonna do? Draw layers. All this stuff seems to work okay. Draw tree is the one that's failing. And it's because the draw weights command is not for some reason drawing the weight. Now, the question is root.ori a thing? It is indeed a thing because we use it up here. Root weight. Weight is root weight. We have a weight. We definitely have a weight. In fact, let's output the weight too. Why not? What else am I doing? Let's go here. Let's make it. We are outputting. Yes, so the weight is 1. Weight text is 1.0. We are outputting everything just fine. That's not a problem. Okay, so we have the weight. grow circle, draw weights. Let me see, char test. Are we allowed to manipulate? Let's see, animation, 0.25. What do I do next? Where do I grow the circle, giving it the appropriate animation. Let's go down here. Let me see, maybe animation, size t, I equals 0. Oh, maybe this is it. I equals animation.current frame. Now let's go here, make. And let's see what happens here. Wait, you're drawing a circle after the weight. Circle is probably being drawn over the weight. Oh, you're totally right. Yeah, you're right. Let me check. We do grow a circle. No, we do grow a circle. Wait. Let me think. Okay, 1 second. Delay 5 loop 0 frame animation.png. Let's take a look at this. Then we do Mirage animation.png. Yeah, wait. Let me go up to the top real quick. And let me see. Draw encoding. That's fine. Draw weights. Placing text in circle. Cairo text extends. Cairo show text. That's fine. So we're growing the circle here. And then we're putting it in here. So we're saying J less than number of frames plus J. Cairo set source. So yeah, we're setting the source to black. Cairo text extends T, text box, animation frame context J, test, text box. Else root or EX equals left. What's that? Oh, okay. So the circle is probably being drawn over the weight. We're drawing the circle first, I think. Because we are putting a letter on top of the circle at the end. So maybe if I just put draw weights. Weird. Maybe if I put draw weights under this somehow. So let's go here. Just drop it down there. Remove it from up here. But I don't think this should change anything. Let me go into the make file real quick. Let's not make an animation anymore. So vi make file. Yes, now let's go down here. And let's do this. So we're not going to make it into an animation. We're just going to make it into a bunch of images. So let's go here. Write that. Go over here. Make. And give it a second to run. Now we're making all the images. Man, this shouldn't change anything. Why would it change anything? Okay. So now we're going to go into Mirage image. No, it didn't change anything. Dag nabbit. Okay, so remember how I said at the very start of today's episode that we're going to start working on dynamic Huffman encoding? Remember that. Because it might not happen. Okay, so draw tree, frame, animation. That seems fine. Let me see something. Let's go to the very top. That was not what I meant to do. Very top. What am I doing? There we go. Top. Now we're going to do draw weights, animation, weight, position, origin. Okay. Down at the bottom, draw weights, animation, double weight, position, origin. Do we need to increase the current frame or something like that? Let me think. For size T. Why not? Animation.current frame plus equals 1. Make. This shouldn't do anything. We're just adding a frame. Yeah, I can't imagine it would. Should this do anything? Let's go over here. Let's do Mirage. No. Okay. I thought maybe because we didn't have a frame in there. Okay. So that clearly doesn't do anything. Let's go over here and let's think. We're changing the font size. That shouldn't matter. Changing it to white also shouldn't matter. Let's see. Position origin. Maybe I'm just not putting it in the right spot. Let's change the origin to something else. Okay, let's write this, go over here to make. Kara stroke, Kara show text. Everything's fine. Raj. Okay, so the position wasn't wrong. Let's scroll up. Let me see. What did I do over here to draw text in the circle? So Kara set source RGB, animation frame context 000. Exactly what we had before. Text box. Kara move to the appropriate location, which we did. Kara show text. Kara stroke. Draw weights. Huh. It looks to me like this is exactly what we did before. Animation, current frame. J lists the number of frames plus plus J. What am I doing here that's different? Kara set source RGB, animation frame context J 000. Kara text extends text box. Huh. I'm not seeing it. Let's go down to the bottom. So Kara set font size. Let me run this. Mirage. Frames. Animation.gif. Just have it up there on the side. Huh. No numbers. Let's not change the font size. I'm just trying like everything now. That was not the right commenting scheme. This is the right commenting scheme. So, set source RGB. Let's just try a whole bunch of random things. Write this, go over here. VI make file. Convert. Make. I don't think this is going to help any. I'm clearly missing something obvious. Wait texts. Wait text is outputting. Kara font, set font size. Changing the font size shouldn't matter, right? You'd think it wouldn't matter. Let me see what happens if I just put this into the loop above. 1 second. Once it converts this and we show that it's not working. Yeah, not working. I'm just going to take this loop and I'm going to put it into string weight, position origin. Yeah, I'm going to put it into 1 second, draw tree, draw weights. I'm going to put it into this here. And we're just going to see if it works. So we've got to add in a couple spaces. That's fine. The more efficient way to do this, I don't care. Okay, so wait text. std2 string, what do we want? We want root pointing to wait. Animation frame context of I. I think all these I's need to be changed to J's for some reason. I'm not sure why. Why am I using J? If, I guess I is fine. Okay, frame context of I. Animation frame context, all seems fine to me. So now, instead of doing origin, we do root origin. Pointing to origin. Root pointing to origin. Anything else we need to change here? Wait text, animation frame context. I think that's all fine. Let's write this, go over here, and let's make it. Okay. Doing it twice, that seems fine. And let's see. Give it a second. Just a quick second. We're almost there. Sometimes it's weird. This stream, I just have to wait for an image to make. Yep. So, how's everyone? Ah, there it is. Good. Don't have to make awkward conversation. Okay, this didn't work either. Question is, why didn't it work? You need to download more RAM? I've got a lot of RAM. Okay, so I'm not sure why this didn't work at all. We're outputting the wait text. The wait text seems fine. Let me try changing all these I's to J's. Why not? Because I have absolutely no idea what else could be the problem. J. Let's see. J. j. Let's look at the difference between these two loops. There has to be something that's different. Okay, so what's going on here? Placing text in circle. For int j size tj, change it to an int. Why not? Because I have absolutely no idea what's happening. Int j. Okay, int j, animation current frame, j less than number of frames, plus j. Fine. Cairo, set font size. Besides the color, yeah, everything else is basically the same. Cairo text extends t. Cairo text extends. That seems fine. Weight text, also fine. Text box, all right. Cairo move to, animation frame context j. Yep, that's the same. Root origin x, root origin y. Also should be fine. Cairo show text, Cairo stroke. Yep. Yep. So why is one showing and the other not? Let's try changing this to a different name. So let's say text box, I don't know, 2. Text box 2. Where am I? Drop text. Oh, this shouldn't matter at all. Bah. That's annoying. Try it again. I know, first sign of insanity is, you know. Let's try just writing a random letter. Okay, not gonna worry about this, just writing a random letter. Maybe it doesn't, maybe there's something else it doesn't like. So, let's see what happens. One second, let it write. Yeah, maybe it doesn't like this whole weight text thing. Mirage? Nope, we're not even drawing anything. Why? Oh, again, maybe because of the weight text thing. Okay, let's go here. Let's try changing this to something. Can we just write it in here? I'm not sure. Is this allowed? I have no idea. Let's see. No, it doesn't like that. Invalid conversion from int to constant char star. Are we allowed to do this? Probably not. I think it doesn't like double quotes. Because I think I tried this before. Is it fine with double quotes? Oh, okay, that's fine. Alright, give it a second to make this. Hopefully we'll have a big ol' hey in front of everything. We'll see what happens. Okay, one second. Thanks, Guster and Zadiston. You guys are great. Okay, one second. Let's see what's happening here. If this doesn't work, then I'm at a complete loss. I have no idea. Ah, fair enough. Yeah, I knew that. It's somewhere in the back of my mind. Okay. Now let's do Mirage animation. Yeah, okay, so there's all our haze. We got a lot of haze. Okay, so it doesn't like this 2-string guy then. Not sure why. Hey, Zadison. Okay, so the haze are being drawn, which is good. It's something's working. So here's what I'm going to do. I'm going to leave the font size exactly as it is before, or as it has been. And I'm going to change how we're drawing these guys. So draw weights. Let me see. Yeah, okay. I'm going to change how we're drawing these guys. What I want to do is put hey underneath each of these guys. And I want to see how that looks. Just for the record. So Ori X is going to be the exact origin location. Ori Y is going to be plus. Then we want 12 plus root. Yeah, I'll change it in just a second. I think I know what I'm going to do here. Let me go to draw weights. And let's just change how we're drawing the weights down there. Since we already have the function, let's use the function. We're going to remove this. We're going to remove this. We're going to say ori x is fine plus 12 times weight times, wait, what? Plus 12 plus weight times 0.5. Don't ask, this is what we have. I don't think that's true. Okay, so let's go here. And let's change it. So let's write down hey here. Hey again, and hey again here. And let's do make. Okay, give it a second. Okay, so now what we need to do is one more thing. Only thing, what do we need to do? We need to add in a few more things. So where's our drop text? Here it is. I don't think so. I don't think it is. Here. We're putting it in another location, and we'll see. So let's change this back to weight text. Let's go here to weight text. Let's merge animation.gif. So here, we clearly see that we have hey under each of these guys. In fact, let's make it even further and more obvious. So let's do this. Animation frame context, so we want this minus text box divided by 2, I believe is what we want. Yep. Dot width divided by 2. And then here we want plus text box dot height. Then it should be plus double of I times 15 weight. Yes, good. Over here, let's make it one more time. And here we should not see anything. We are not going to see anything. I'm like 95% sure there's nothing here. However, afterwards I'm going to change this weight text back to hey, and we will see hey under each of the nodes. Let's go here. Write this. 1 second. Give it a second to make the thing. Merge animation.gif. Okay, so we don't see anything here. Okay, so now I changed the string to hey, and let's do that. In fact, here's what I'm gonna do. CP. Let's do frames animation.gif into animation nothing.gif, and now let's make it one more time. And we should see hey under each of the nodes. Give it a second. What? Famous last words, or it would be more obvious if the text were black? How is that famous last words? Huh. I'm not sure. I have no idea why this is doing this, but we definitely will see hey under each of the nodes. I have absolutely no doubt about that. And I'm going to use that in just a second, because I also want to place one more thing under each of the nodes. And then I want to see what happens. I want to see if we can visualize this in another way. So let's do merge animation.gif, and we are clearly seeing hey under each of the nodes. So, yep. Okay, so now I want to try something else real quick. I want to do std string weight text equals std2 string weight. Yeah, let's try that. So we want std string weight text is equal to 2 string, and then we go down here and we say weight text 2 string. That might work. .c string. And let's go down here and change that. Where's weight text? Here. To str. Okay, let's try this. Make animation Oh, I'm sorry, C string. What was I thinking? C string. Make. Okay, this maybe will work. I'm not sure. But the other thing too is I have to find a way to truncate these guys so that they aren't so big. Thanks, Addison. I don't know what I was thinking. Because I used it correctly up like 2 lines or 4 lines up. I used it correctly. 5 lines? Whatever. 5 lines, burgers and fries. Best. Best place to get your queue ready. Okay, 1 second. $2.99. Almost there. Give it a second to make the animation. Now I have to figure out a way to get wait text truncated so we don't have the decimals. So let's see. Mirage animation.gif. Yeah, okay. So again, this is working. We just have to find a way to make it a little bit more visually appealing, and that would be done pretty easily. So let's go here and let's do that. With this stream delay, by the time you see our messages, you've already fixed it. Well, with some of them, yeah, but with others, it's super obvious. There's nothing I can do about the stream delay, guys. There's always going to be stream delay on Twitch. I wish there wasn't, but there is. Okay, so we have to add one more thing in here, and that one more thing is the following. So we're going to do Cairo show text. Let me think. And I have to add in something else. So now we're going to do... I don't want to do Cairo show or stroke yet. I want to do this. So now we're going to say Cairo text extends T. T. And I'm going to call this underscore text box. Maybe we should do a line instead. Let's just do horizontal line. Line box. Look at me with my great naming schemes. Okay, and now we do Cairo. Text extends. Animation.frame context of I. And then we want the following. I'm just going to put in a single dash for now. You might have to use sprintf after all, given how you can't specify precision in toString. Can we not? I'm not sure. Okay, so let me see. Then we want at. Just place a 0 at the position you want to truncate it at. How do I do that? Could be worse. You could be naming your variables. Yep. I should do that. Okay. So what do we want to do next? Text extends. What am I doing? Text box. So now we want at line box. Okay. So we have that done. Next, what do we need to do? We need to do Cairo move to. And here's where things get fun. We're going to move to here, but we have to give it a specific Y location. That's not this Y location. It should be ori Y plus textbox.height plus double of I times 15, which is the size of the text. And I admit this could be done way easier. There's a variable number of characters before radix point though. Before the radix point. I don't know what a radix point is. Sorry about that. Textbox.height plus 12 plus weight times 0.05 plus, let's say it's going to be 15. Let's say. And then let's go up here and say this is double of I. And then we add 2.0. Plus 2.0. Okay, let's see what happens here. Then we have to do Cairo show text, and that should be that. Here we are. So Cairo show text, and let's do animation dot frame context. 1 second of I, and then we want this, and let's make that. Frame context was not shown. 1 second. Okay, so then this should fix another problem that we have. And now it's just a matter of figuring out how to fix the last problem we have. And we'll see if we like the weight under the nodes once we have this done. I think the weight under the nodes is the most obvious option here. Weight text log 10 of weight plus 1 equals 0. Wait, what? Weight text, log base 10 of weight. That's okay, Chocolate Bagel. Thanks for coming in. Actually, one of my best friends' nickname was Bagel. I don't know why. It just was. That's his nickname, Bagel. That's okay. So let's do mirage animation.gif, and let's see what we got. Okay, we're drawing all the lines. This is doing something different than I thought it was going to do. Huh. Yeah, that's way different than what I thought it was going to do. That's because this needs to be a line box. Zero hack was bad enough. Wait text. Oh. Let me think. So how am I gonna, so log base 10 of weight plus 1. Would that work? Wait text. Let me think. Oh, well, let's check this one real quick. Write this, go over here. And let me do... No, that's not what I wanted. Sorry about that. Let's make it one more time. Make. Okay. So what we're saying is wait text of log 10 base 1 equals 0. Where do I put that one in? Give it a second to make the new animation. So luckily the line and text box heights are the same, which is fine. Okay. So let's see what we need to do then. We need to truncate a string, right? So we have to remove everything that's outside of 0. I'd recommend against actually using that. Maybe. I just need to think about what I need to do. Okay. We have a string. We want to truncate everything outside of the string. So we want everything that's after the decimal point gone. So let me see. Mirage animation.gif. Let's see what this looks like. We have... Oh, it's just so ugly with those weights looking like that. That's fine. Let's also do the following. Let's do this as plus 1. Should actually be plus 2. I don't know. It's hard to see. Let's see. What else do we need to do? I think this will look okay when we get it done. I just have to think about it real quick. So let's change a couple of different guys. In this case, it removes the decimal point. I want to remove the decimal point. So let me think. What am I using here? I'm using toString integer. Let me see. toString int value. I guess because weight's a double. What if I just change this to an int? Because it's always going to be an int. Make. Yep, that fixed it. We're done. I don't see anything after the decimal point except zeros, so I don't see the problem. All I had to do is change it to an int. We're good. Because, again, weight is always going to be an integer. I just kind of realized that now, but that was kind of my bad for not realizing it before. Okay, so now we'll take a look at what the animation looks like, and we will go from there. We can decide at that point. Sorry. My bad. I feel kind of bad now, but that's okay. Let's go to mirage animation.gif and let's see what this looks like. Okay, so on the one hand, I think we need more dashes or something like that. Or we could just remove the dash. Let me think. What if we just remove the dash for now? I don't know if I like having the weights there or not. I think it looks kind of weird. Yeah. Yeah, let me see. Go here. Let's go to make one more time. It looks super cluttered with that. How's another way to do this? Yeah, I feel like we do need to visualize the weights, but at the same time that looked really, really, I don't know, I liked it without the weights better. I don't think you should be drawing the weights at all. Hmm. You're already visualizing with different leaves and color sizes. Yeah. This one without the line doesn't look so bad, but it is pretty cluttered. So here's what I'm going to do. For now, we're going to leave this function on the side. So let's go here. Let's change this back to just double of I. Yeah, you're totally right. But I'm going to leave the draw weights function in there because why not? Yeah, so it's going to be there, but you're right. I think it looks better without it. Maybe. So let's go here. Let's do this. Right, and let's do make. Dang it, that was a waste of a whole day. But that's okay. Perfectly okay. That's how it goes sometimes. Okay. So now we can take a second to start talking about dynamic Huffman encoding, which will probably take the rest of today's episode. So, that's... Why are you even casting I to a double there? Because when I originally put the weights into this code, I wasn't sure what the weights would look like, so I thought they'd be doubles. But in fact, they're probably integers. So I should probably go and fix that. However, let's talk about dynamic Huffman encoding, because there may be something else there. So mirageanimation.gif. Yeah, I think this might still be as good as we can get here. It looks good. Don't get me wrong, I really like it. I think it looks great. It's just... I don't know. In the position calculation. Why are you even casting I to a double there? In the position calculation. 1 second. I'm not sure where I'm casting it to a double. You're talking about up here for the text box height? There? I don't know. Why not? I guess it doesn't have to be. I just keep getting bitten all the time with integer logic. And I used to not ever, and now I am all the time, and I don't know why. Okay, that's fine. I can remove that. Not a big deal. I probably do that a lot, actually. Double of R, set source RGB. It's fine. Yeah, I cast a lot of things to doubles. Just because I keep getting bitten by integer logic. We can fix it in a little bit. Let's write this, go over here, let's make it. Okay, so let's spend the rest of today's episode talking about the dynamic Huffman encoding algorithm that I've been working on for the past little bit. Not working on, rather I have been learning about. I have not actually been making this one up. I have to clarify that. This was made by someone Vitter in 1987, I think. Let me see, I've got his paper right here. It is, 1 second, flipping through the pages. How did I flipped through all the pages and somehow I missed the first page. Okay. Yep. Yeah, maybe I cost it too much. Okay, so Jeffrey Scott Vitter. Now, here's the thing, guys. If you look up the Vitter algorithm on Google, this is actually kind of interesting in a way. You look up the Vitter algorithm, you will find something like this. So let me see, the Vitter algorithm. Okay, and it will be best algorithm no one knows about. Okay, so best algorithm no one knows about. I know about it because I read this article. Here's the article I'm talking about. It doesn't matter. That's the wrong Vitter algorithm. This is not the algorithm I wanted. So here's his paper. It was written in 1987, I believe. Yeah, 1987 down there. The one that we want is... One second. Again, 1987. This one is in October 1987, though. It is design and analysis of dynamic Huffman codes. So let's look for that. Design and analysis of dynamic Huffman codes. When I Google it, I get an answer like this. To make 3 decimals, double truncate. Ah, fair enough. Okay. What am I looking for? I apparently misspelled analysis. This one maybe. Am I allowed to look into this PDF? I don't know. One second. We'll see. Design and analysis. No. Okay, so apparently, let me see. Yeah, apparently you have to get this one on a campus of some sort. Algorithm 673. Dynamic Huffman encoding. This is not the one. Let me see. Yeah, apparently you have to access it. Well, yeah, it truncates the value, but it also turns it into an... Oh, I thought it turned it into an integer. We'll see. I'm not sure. Anyway, so the paper itself is by Vitter, 1987, October. That's fine. Just letting you guys know that's where the paper is from. Now, let's take a minute to talk about what it does. And this might take longer than the amount of time we have left in the episode. Keep this in mind, because I'm not intending... I thought this was going to take forever to describe, and it might take forever to describe. Let's take a look at this last animation just to make sure everything is good. So we're going to do mirage animation.gif. Let me see. Yeah, everything seems fine over here. Yep. Okay, this is not the same paper. But this is the Pascal implementation of the paper, so I guess it's pretty close. But this isn't the one that I'm looking at. Okay, so let's talk about it. At the very start of today's episode, I spent a little bit of time talking about new page before, Huffman algorithms. And what you have to do what we just did. So the animation you have been seeing throughout all of these episodes is of the poem or whatever it is. Jack and Jill went up the hill to fetch a pail of water. Jack fell down, broke his crown, and Jill came tumbling after. That's the animation that we're currently working on right now. What we did is we went through and we we went through and we counted all of the frequencies of all the letters appearing, and then we created a Huffman tree from that. That worked okay. Now the thing is, it's not going to work well in all cases. So what we need is a dynamic way to create a Huffman tree that works for incredibly large alphabet sizes and incredibly large phrases. And this is where dynamic Huffman encoding comes into play. Huffman encoding. Okay, so if you're like me, you might think the naive way to do this. You might think of this in a rather naive way. So let's say we have an A. Let's read in a random string. A, B, B, C, D. Okay? So let's think about this in kind of the easiest way possible. We have a root node. The root node currently has nothing in it. Okay? So now we add in an A. The A is added in here. And what we'll do is we'll say, okay, A now has a weight of 1. Okay? And we have an additional node here, which is a 0, right? Because it has to be a binary tree, we must create that other node. And we update root to have 1. Research 8, dynamic. Yeah, that's it. This is it. Oh, yes, that is actually it. Yep. That's the exact paper. I don't know how you found it, but good work. That's the paper we need to work on. I'm going to star this so I can link it later. Okay. So we have A of 1. Now we go further. We say, okay, we have A of 1. Now we have to do B. So B, we increase the weight of the total tree. We have A still as 1. But now we have, over here, we have a B, which is now 1. And we have a 0 here. And this is of weight 1 in here. Okay? So the next tree you'd think, okay, well we have 3. We have A of 1. Okay. Then we have 2 here. We have B of 2. And then we have another 0 node here. But you know, it makes sense to switch these two around because A and B, B is now more than A, so we want the most frequent one to have the least number of bits. So this is now B2, A1. And then we go further. We say, okay, well now 4, I'm really bad at drawing these guys, so let's say 4 is now going to be B2. That is a 2. Yep, that's a 2. Then we go down here, and we say, okay, well now we have a 3 here. Then we do A1, go down. Then we have, oh, I'm sorry. That changes back to 1. This is now 2, 1. And we do C, because C has just been added, 1. And then we have another 0. And then finally, the last tree, which I don't know where to draw, would look something like this. I'm drawing it on a new page. 5. We have B2, 3, A1, 2, C1, and then D1, and then 0. And 1. Okay, so this would be one way to draw a tree, right? This is kind of sort of following an algorithm that's known as FGK. It's for 3 people's names. And that's fine. It works okay, right? So B is the highest one. If we go through, we say 1, 0, 1, 0, 1, 0, 1, 0, like we did with the static Huffman tree. And as we're going through, this is perfectly okay, right? We have B as the most frequent. It has the least number of letters. All of these guys have more letters. It's fine. However, Foolishly Gaming, did you go to art school? Because this is beautiful. Thanks, man. I did not go to art school. I went to science school. So, no. Okay, now this is great. It works, kind of, okay? Now, the thing is, if we want to continually update this tree, sure, okay, this is kind of what you'd expect. You just go through, you count how many of each letter there are, and if, for example, there's more A's than B's, then you switch to A's and B's. You just move the tree around, and manipulate it so that the more frequent your character is, the higher up on the tree it appears. And that makes a good bit of sense. But now let's think about this in another way. Okay, the algorithm that we're going to be implementing is the Vitter algorithm from 1987, and I'm going to specify October. I think it's October. I'm going to say it's October. Okay, October. This algorithm is much faster than the previous algorithm that was out there, which is the FGK algorithm. Again, quite similar to what we just did. Now, the Vitter algorithm is a little bit weird in that it has a few different things that you always have to keep in mind. So let me go ahead and talk about these different criteria. So let me see if I can find it. It's on the paper that was just linked in chat, and it will be on page, one second, I can't seem to find it. Where is it? Theorem? Lemma? Screw it. We're going to Wikipedia. Of course, Newth would be K. Yeah, probably. Okay, so let me go here. Let me just find it on Wikipedia. So dynamic Huffman encoding. Now, I know what you're thinking. If it's on Wikipedia, why was it so hard for me to figure out? This is like one of the poorest written Wikipedia articles I've seen in a while. Okay, well, it's fine. It's not that big of a deal. Okay, so there's 4 things to keep in mind. We have implicit numbering, invariants, blocks, and leaders. These are the things we want to keep in mind. So let's go one step at a time. First of all, when we say implicit numbering, what do we mean? Implicit numbering. There we go, number sign. So let's say we have a tree. I'm not going to draw anything in the tree. I'm just going to draw the tree itself. So we have something like this, and I don't know, I'll add an additional guy down here. Implicit numbering says this: the highest numbered character in this tree is going to be 1, 2, 3, 4, 5, 6, 7, 8, 8 here. Then we have 7, 6, 5, 4, 3, 2. Oh. Pretend I can count, guys. 1, 0. There we go. Okay, so here's the idea. With the implicit numbering scheme, we read from left to right and from bottom to top. So the idea is that these numbers, they're actually incredibly important to remember. These numbers allow us to tell where the nodes are with respect to other nodes, okay? Now, let's go ahead and fill weights into these guys. So let's say we have a weight of, I don't know, I'm just gonna make up some numbers. We'll say 1, 1, 2, 3, 4, okay? Maybe you guys can't draw this, see this, 3, 3, 4, okay? So that means this is gonna be a 2. This is going to be a, let's see, 4. This is going to be a 7. And this is going to be an 11 up top. Now, we have this next concept, which are known as blocks. Blocks. Blocks are any number, or rather, they are values that are shared between all of the, any nodes that have the same value are going to be in the same block. How about that? So for example, these two 1s are going to be in the red block. There are no other 1s. These two 2s are going to be in the 2 block. There's only one thing in the 3 block, 2 things in the 4 block. I guess we can do this one pink. 1 thing in the 7 block and 1 thing in the 11 block. So that's kind of how it works. The blocks are simply, anytime you have the same number in a node, it's going to be in the same block, okay? So the idea then is that you have a leader of the block, which is the highest numbered one in the block. So that means, for example, which color did I not use? Blue? The leader of the 1 block is going to be this guy right here. The leader of the 2 block is going to be this guy right here. The leader of the 4 block will be this guy right here. Again, the leader is going to be highest numbered member of the block. Okay, good. So hopefully you guys can read my handwriting. If you can't, that's too bad. I could try to fix it in a little bit. Okay, so we have these things. Implicit numbering, which allows us to define the leader in every single block. And then we also have blocks themselves. Okay, so now the last thing we have to mention, which is one of the more difficult things to understand, is the invariant. On Wikipedia, it's stated rather simply. It says, let me just go over there. It says, for each weight W, all leaves of weight W precede all internal nodes having weight W. What does this mean in practice? That's your fan? Hey, what's up? This means that all of the internal nodes have higher numbers than the external nodes. So if we go back here, all of the internal nodes in a block must have higher numbers than the external nodes in a block. Now let me think. Is that how we did it? Yeah, it should be how we did it. So let's go through and redraw that tree that we just had. The tree was 1 page before. And you'll note that this invariant is actually not correctly held. Because we have these 1-1s, that's fine, because these are both leaves. But here, we have a situation where we did not follow the invariant. So this is not an appropriate tree, because this internal node has to come after this external leaf. So to redraw the tree, keeping in mind this invariant, it looks like this. It will be, let's see, it was 11. Then we had, what was it, 4, I believe? Wait, let me think here. Also, these 4s need to be swapped here and there. So we'd have to swap these guys here and these guys here. Okay? And this is kind of confusing here. Actually, this entire algorithm is kind of confusing. So forgive me if I'm running through it kind of quickly. I think this becomes more obvious when we do an example. So how about this? Instead of rewriting this tree, which was just kind of randomly fabricated on the fly, let's do an actual encoding here. So let's do page, new page before. The last thing we need to talk about before moving any further is this thing called increment. increment, and slide. Actually, shoot, I did it backwards. It's slide and increment. My bad. Slide, and increment. Here's the idea. I'm going to draw leaf nodes as squares, and I'm going to draw circle nodes as internal nodes. So this is a leaf node. We're going to say it has a value of 4. This is an internal node. It has a value of 4, and these guys are connected together here. We have a couple of different nodes in between, a whole bunch of random nodes. Then we have 2 internal nodes, 4 here, 4 here. And then we have 5 as another leaf node over here. So this is kind of what you could expect. Now, in practice, this looks a little bit different, right? So this would basically mean that we have some sort of tree, and the tree, there's some sort of Y dimension here that we're not taking into account. So for example, this group here could be down here. So it could be 4, 4, somehow connected here. And then these guys up here could be somewhere here, 4, 4. And 5 could be somewhere over here. I don't know. The tree itself has a whole bunch of random things going on around here that we don't really know about. But that doesn't really matter because of the implicit numbering scheme, right? So what we've done, in case you guys are kind of curious, all of these guys here, all of these 4s, they're all blocks. This is one block. And then we have the 5 blocks starting out here. Okay? So the idea is that we've organized these guys into these blocks. Now, what we're going to do is we're going to say that we want to update this block right here. We want to update the 4. So what we do is we move to the front of the block over here. So the start of all the 4s. Okay? This pushes all of the other 4s back. So it's going to make the new, I guess, the new tree look something like this. So now this internal node has been shifted over. So there's a 4 there. We're going to assume there's another internal node here. And then we have, let me see, this internal node shifting this way, 4. And we have the external node here. Okay. And now we have 5 here. We then increment this guy. So we slit it. Now we increment it to be 5. And then after incrementing it, we then update the next guy, which is going to be here. The next guy we increment is up here. And then we follow the tree forward. So basically we go through the tree, we update a single node, then we update all the nodes up to root. So we keep updating all the trees further and further up. So this is if we update a leaf node. If we implement, or if we increase a internal node, things are a little bit different. So when we get here, we're no longer working with a leaf node, we're now working with an internal node. Going up the tree, internal node is next. So how do internal nodes work? Well, let's go page, new page before. And I'm following this directly from the paper that was linked in chat by Zadiston. Okay. Now, this one's a little bit harder. So internal nodes. These are not so much harder. They're basically the same thing, just a little bit different. So we have our internal node. We're going to call this a value 8. And we're going to say it's connected to a leaf node of value 9. Okay? So it's just about to break into the 9 block. We have a whole bunch of leaf nodes here. 9. And then we have an internal node here. This is why it's a little bit confusing. And I'm actually going to draw 2 leaf nodes of 9 here, just to completely follow the paper. And we're going to assume this one is this way. Okay, so for this case, what we do is we move it along the block, but this guy only moves to this location, the location of the first internal node. And the reason it does this is because of that invariant we said before. The invariant of saying that all internal nodes must come before all external nodes in the same block. So we're saying all of the internal nodes must come before all of the leaves, or have a higher number than all of the leaves. Okay, so we move this over here. Tree shifts. So now we have 9, 9, something like this. Dot, dot, dot. 9, 9. These guys are connected now because all of these guys have been shifted to the left. And then we have the next internal node here. And actually, wait real quick. This is still an 8. We then increment its number to be 9. And then instead of updating this guy, we actually go back and we update this guy. And we move along the tree that way. And that's the 2 nodes here. Now, to end the day, I'm going to show you guys a quick example of how to do this. And what we might do tomorrow, guys, is we might spend another 30-45 minutes just going through this algorithm one more time with another example. Because this is, again, not trivial. It took me a very long time to understand. So let's encode a super simple... I don't know what just happened there. Let's encode a super simple phrase. The phrase is simply going to be A, B, C, D. So like we did before, we're going to start with something that is not yet translated. Okay, this is going to be the starting node, and we're going to call it the 0 node. Okay, so what is the first thing we do? The first thing we do is from the 0 node, we keep this node 0, we add a 0 node over here, and then we add an empty node, which is A, also 0. Okay? So now we just fill it up. We do the increment and slide things. Luckily, there is nothing in any block here. So we move this 0, which is the one we update first, to the start of the block. Well, the block is 0, so it's already moved to the start of the block. This guy updates to 1. Then we update this to 1. Okay, so now we have A. Next step is B. Okay, we do something similar. We have 1, we have A1, go down here, add a 0 node, add a B0 node, and then add a big 0 node in here. Okay, that's fantastic. Now things get a little bit complicated, and I'm gonna pull out make child nodes, I'm guessing? Make child nodes, yep, that's what we're doing. So we're making 2 children nodes, B0 and a big 0 in the end. Okay, so now things get a little bit more complicated. We have this, but now we need to move this 0 to the start of the blocks of 1, right? So this means that this 0 needs to flip with this A right here. Okay, so in order to flip it to that A right there, it's not so bad. We just do it. So this turns the new, one second, the new tree into the following. What exactly are you doing with that tree? What tree? Which tree? Which tree are we talking about? I was trying to explain everything as I went along. Which tree are you talking about? Anyway, so now we're going to shift this tree over here because again, we have to increment it and slide. So we move it, the next block's 1. We move it in front of all of the leaves in block 1. So this is going to go over here. So we now have our 0 node here, our B of 0 here, our big 0 here, and we have A here. The 0 to A1 0 tree. 0 A1 0 tree. I'm still kind of confused as to what you mean. I am going through and I'm doing the Vitter algorithm, the dynamic Huffman algorithm, in order to show that this will create a tree that we need. So the idea here is, again, we're following the same that we did before. Let's go back real quick. Invariant, no, we want to go this way. Internal nodes. So 8 moves in front of all of the 9 external nodes of 9, and then it's put right here. So it moves through all of the internal nodes, and then here, and then we increment it afterwards. So it comes before all of the, external nodes. 8 moves in front of all the external nodes, and moves in front of the first internal node in that block. Okay, so that's what we're doing here. So let's go back to 3, I believe. So we have 0 here. The next 0 plus 1 is 1. So we move in front of all of the external nodes of 1, and then we shift the tree over here. Okay, now, this is obviously still a 1. However, we now need to update this. So this becomes the following. 1, 1, 2, 1, 1. So B now has a 1. Okay, so now the next part is where it gets confusing. We have to do the following. So this is a 2. Okay, this is an A1. This is a 1 with a B1 over here. 0 with a C0. And 0 over here. So now we've done the same thing we did before. We have 0. Okay, so now we have to increment and slide, right? Which makes complete and total sense. However, this is where it's a little bit annoying. Let's think about the implicit numbering here. So let's go down and I'm gonna add the numbers in here. We have 1, 2, 3, 4, 5, 6 nodes, 7 nodes. So this is gonna be 6, 5, 4, 3, 2, 1. Let's put these in a different spot so that it's a little bit easier to see. 1 second. So we're gonna say 6, 5, 4, 3, 2, 1. Oh, 3, 2, 1, 0. There we go. That's all the nodes. Okay, so I had to look up. That's what I was missing. I had to look up Huffman tree. I just joined, so I wasn't sure. Oh, sorry. We're going through the dynamic Huffman tree. Again, we've already done the simple Huffman trees. Okay, so now we're looking at the implicit numbering. So we have to move this internal node right here in front of all of the external nodes that have weight 1. Well, that means we have to move it in front of here. Okay, so that means 4 has to shift to 3, and 3 has to shift to 2. So this guy is going to move up here. This guy is going to move over here. And this guy is going to move over here to make the new tree look like this. 2. Hey, Frank. It's okay, Frank. Just be careful. Because, again, you have a tendency to be a little bit too rambunctious in chat. Okay, so now we do this change. This is still connected to 1 over here. Except now we have everything else different. So we have this connected to our 0 node, C0. This is still our big 0. Then we have down here, A1 and B1. Okay, so this is our new tree. All we have to do is update this guy because it's already been slid, and we're set. Now, when we add in the D, things is the slide because of the position weight of the string. Yes, so it's due to the weight. No, it's just, again, Frank, you just, it's fine. Just be careful. Okay. So then we have to increase this guy to 3, and that's that. So yes, Patrick, the slide, it is slid, and then it's incremented. It's part of the algorithm. And Frank, those are the types of comments that you can't say. Please be careful. Don't attack people, you know, because that's clearly a false statement. Gustorn doesn't hate you. He doesn't think you're a noob. And he did, so far as I'm aware, didn't really get angry. It's just, it happened. Okay, so now we have to add in the D. When we add in the D, oh, I'm sorry, this also updates to a 2. My bad, I failed at that one. So this updates to a 2. Okay, so now we have to add in the D. And the D is going to be a little bit hard here. So let's do page, new page before. And I'm just going to write down the tree that we currently have. So we have 3, 2, A of 1, B of 1, 1, C of 1, 0. So the D is going to be added in here. So let's do 0, D, 0, 1. Okay, so this Huffman thing is about compression. Interesting. Oh. I'm sorry, Math. I did not realize you hadn't been here for the past 2 weeks. We've literally been doing the Huffman algorithm for the past, like weeks or so. Okay. I don't think it was, I mean, Huffman's super old. It's one of like the original data compression algorithms, I thought. Okay, so what do we need to do here? This now needs to be moved to the very front block of all of the ones. So what does that mean? That means it needs to be moved over here. Okay, and everything else needs to be shifted this way. So the new tree is going to be the following. It's going to be 3, 2, 2. Actually, this is updated, so this is now 2. Then we do this. So we add in 1, D1, 0. Then we do A, 1. B1, C1. And that is the final tree for A, B, C, D. And you can see that this is significantly more complicated than anything else that we've done so far. And this, let me see. I think it was used for text encoding before. Yeah, I think it was. Again, this is like way old. This is back when like Shannon was still around. This is like Fano and a whole bunch of people like that. So I think Huffman was a student of Fano and came up with this idea. Anyway, so this is one of the simple cases of this algorithm, and this was only moving around internal nodes. We haven't yet talked about external nodes, which we'll do tomorrow. So this is kind of a teaser for what we're going to be doing in the future with the dynamic Huffman encoding scheme. I'm actually really looking forward to this. I need to figure out how to visualize it and draw it and things like this, because honestly, it's not very well kept. It's really hard to find this algorithm online, and I think it's going to look really cool. For the record, in case you haven't been here, we do have this ability to draw our Huffman tree for data compression over here, and that animation looks pretty good in my opinion. Okay, so to recap what we've done today, we spent a good bit of time trying to visualize the weights in a different way of each of these extra nodes, and we kind of sort of failed. Well, we succeeded, but we didn't like it in the end, so it kind of didn't happen the way we wanted it to happen. But that's okay. That's how coding works. That's how life works in general. And what we're doing now is we're working on dynamic Huffman encoding scheme. If you want more information, feel free to come tomorrow when we talk more about it. But I think tomorrow is going to be a lot of pen and paper. A lot of pen and paper to make sure we fully understand how the algorithm works and things like that. And then after that, we'll go from there. You do hacking hashed passwords with that tree. I do not. I do not at all, Frank. Okay. Anyway, guys, that's it for today. It's 7:06 in the morning, which is a little bit past the time I typically end my stream. So guys, have a great day, night, afternoon, morning, whatever time it happens to be your time. And I will see you around next time for the next episode of Simuleos, where we finally get started with dynamic Huffman algorithm, which again is not going to be intuitive, but it should be a good bit of fun. Unfortunately, I don't do this tree is basically used just for data compression. I don't know what it's I have no idea what it can be used for hacking or anything like that. I honestly, I could care less about hacking. I don't think hacking is a worthwhile pursuit. Anyway, guys, thanks so much for watching. Have a great day, night, afternoon, morning, evening, whatever time it happens to be your time. And I will see you guys next time for the next episode. Zadiston, I could do that, but I figure, I don't know, I think a lot of people know LZM, plus, or LZW is the one I was thinking of, LZW. But, wait, is LZW better than Vitter? It depends. It depends on how you want to look at it. I think LZW is used more than the Vitter algorithm. However, I think both are equally as fast if you do them correctly. I think Vitter is just trickier to implement. Anyway, I just kind of wanted to do dynamic Huffman encoding because it seems really cool, and we'll see what to do. My admins are definitely not hackers, Frank. Again, don't accuse people of being hackers. Okay, so LZW is another compression algorithm. Let me do the LZW compression. LZW compression. Is compression, here it is. Limpel Ziv Welsh or whatever. We might do this. It's a little bit harder to visualize this one. And I think I like Huffman encoding. It's super fun. You can have white hat hackers? Yeah. I mean, I don't know. Hacking to me just isn't interesting. It's like, sure, you can do it, but I don't know. It's just not interesting to me. But that's just because it's not my thing. Okay, that's it, guys. We gotta go here. I gotta go here. I'm kind of late for something. Yeah. Okay, guys, I'm gonna see you around next time. Thanks again for watching. Sorry about delaying this this particular algorithm so long. It wasn't until last night that I really fully understood what the algorithm was doing. So I'm pretty excited about that. So, guys, have a good day. See you guys next time. And we'll be working on this again, where hopefully we'll get a better intuitive feel for how it works. Thanks, guys. See you around. Bye.